All right, so today we're going to be, for the first time, using the second chart. So notice this isn't the one we've been doing, that was 2 pages long. This is the A.3 table, so make sure that you have that out. It was in the same packet that y'all picked up from my mailbox, okay? But go ahead and make sure you have that out. So what we're going to be looking at today is something called confidence intervals, and we're going to be looking at this for the next 2 sections. So we're going to be looking at confidence intervals for a population mean. In this section, the standard deviation is going to be known. In section 8.2, the standard deviation is not going to be known, and we're going to handle it differently. Okay, so let's say we have a whole population of a whole bunch of items, but we don't have the time nor the means to be able to look at everything. Then basically we're going to see how accurate our sample is. Okay, that's what confidence intervals say. So it's literally going to be something like, I am 95% confident that my population mean is going to be in this window, okay, based on what I got from the sample. All right, so X bar, remember, is the mean of the sample. I'm not sure if we've used that X bar notation before. The standard deviation, I think we've used X bar before. The standard deviation of the sample, which in this section we also call the standard error. And that's equal to our population standard deviation over the square root of n. Okay. And then we're also going to look at something called the margin of error, and that is going to be some critical value times the standard error, what we just talked about. Okay, so it'll be a critical value times this formula right here, this sigma over the square root of n. Okay. All right, so let's look at maybe a pretty advanced bell curve here. So let's go ahead and sketch a bell-shaped curve. And we're going to list z-scores down here. So in the middle, z-score would be 0, right? Because z-score describes how far away from the middle we are. And in the middle, we're not any distance away from the middle, right? But I want you to go out to where the z-score is 1.96 to one side or the other. Okay, so remember, z-score describes how far away you are. So it's like we're 1.96 standard deviations outside of the middle. And it turns out this is actually a more exact, okay? That 95% of the values lie in this window. Now remember, before we were saying that 2 standard deviations was 95%, but actually to be more specific, it's actually 1.96. Remember, I told you that was an approximate anyway. So 95% of the values are within z equals 1.96 standard deviations from the mean. Okay, so what we can say is that 5% is outside of this variable or outside this interval, since 100% minus 95% is 5%. So we would say that z equals 1.96 is a critical value. In other words, critical means important, right? So it's a value that we should pay attention to. Okay, so if we want to know what's going to kind of bound the middle 95%, it's actually more specifically a z-score of 1.96. So that's kind of what we're going to be practicing some of today. So let's define a couple of things. So the first thing is, what's a confidence interval? A confidence interval is an interval that is used to estimate the value of a single value. Here, it's going to be the mean. Okay, and the formula for it is going to be whatever your mean of your sample is, plus or minus some margin of error. In other words, we're not going to have the confidence to say that it's a specific value. We're going to have to come up with like an interval. Okay, so some of the examples we've done in the past, we might say if we wanted to make sure that we got the mean, I think we did one on income, right? If we wanted to make sure we got the mean income of Americans in that certain year based on their IRS tax returns, then we might, instead of saying a specific salary amount, we might say we think it's between $45,000 a year and $50,000 a year or something. Okay, like an interval, that's what that means. So it allows us to be more certain because we kind of give ourselves a margin of error. Okay. And then something else that we're going to need to know the definition of is going to be a confidence level. And this is kind of like what it sounds. It's basically how sure do you want to be. But it's a percentage between 0% and 100%. 0% meaning you're not confident at all. 100% meaning you were ultimately confident. But it measures the success rate of the method you're using. In other words, these things take into account that error is a part of statistics. We can be somewhat confident, but we're probably not ever going to be 100% confident. Kind of like when you look at, antibacterial cleaners, they always say something like it kills 99.7% of germs, right? They're not confident to say that it kills all of them, okay? All right, so one of the things that table A.3, that second table that I mentioned we would be using today, so go ahead and get that out. Table A.3, among other things, presents critical values for some of the most commonly used confidence levels. Okay. So if you need to, go ahead and pause the video so you can catch up, because I'm about to cover up these notes just for a bit and show you table A.3, okay? So table A.3, like table A.2, shows a lot of values here in the center. For now, we're not looking at these, but I want you to look down here where it says confidence level. In other words, if we want to be 95% confident, we would use a z-score of 1.96. Notice over here it says z. If we wanted to be 99% confident, we would use a z-score of 2.576. If we wanted to be as confident as we pretty much can be statistically, 99.9% is pretty sure, right? We would have to go out much further from the center, right? We'd have to go out 3.291 z-scores, okay? Notice if we only want to be 20% confident, the z-score is much smaller because we don't have to extend our interval quite as far, okay? So just kind of keep that table on hand. We're going to be using it here in a minute. All right, so let's look at some examples. All right, so let's say that we have a large sample, and that sample has a mean of x bar equals 7.1 and a standard error well, remember this is the formula for the sample standard deviation or the standard error. Those are kind of one and the same. Let's say that came out to be 2.3. So for this one, I'm giving you the values, and I just want you to practice starting to set up confidence intervals for the population mean. So just in a nutshell, what this means is maybe we have a large population and it's not practical for us to study the full population. So instead, we're going to study a sample, but we know that the sample's not as accurate as the population. So we're going to, based on the mean we got for the sample, we're going to make judgments on what we think the mean for the population was going to be with varied levels of confidence. All right, so first let's do a 90% confidence level. Okay, so you need to take out your 8.3 table, and you need to find 90% and look above it, right? It tells you what z-score we need, which is 1.645. So I'm going to write this out in case you forget. But from the bottom row on table 8.3, we see that the critical value for a 90% confidence interval let me look back at the chart. I think it was 1.645. Okay, so that's all we need now to find the margin of error. Okay, so remember the margin of error is going to be the critical value times the standard error. I'm abbreviating to try to fit it on one line. Okay. So here's my answer basically. Let's figure the margin of error first. So the margin of error is going to be our critical value times our standard error that I gave you above. Okay, and if you multiply those out, you get 3.7835. Okay, so remember what this means is this is my error one way or the other. Okay, so if I want to be 90% confident, so the 90% confidence interval then for the population mean, because remember I'm judging the population mean off of the sample mean, is going to be what we thought it was. Notice we got 7.1 in the sample, and then it's going to be plus or minus this error. In other words, it's going to be on one side or the other of that error amount, okay? Or it's, if you actually use your calculator and figure that out, it's going to be somewhere between about 3.3. Remember, mu is the population mean, and 10.9. Okay, so I'm going to circle this. This is normally how you'll write your answer. Okay, so just to recap, what that means is the sample mean was 7.1, but we have to give or take 3.7 on one side or the other because the sample mean might not match the population mean perfectly. Remember, the sample mean is just a smaller group, so it's not going to be perfect. Okay, and the more confident you want to be, the more you're going to have to kind of spread out and the larger your error is going to need to be. In other words, the more spread out from the mean you're going to need to get. Okay, so let's practice a couple more that are maybe higher than 90. So first, look at your table. So look at the table 8.3 and look at the bottom row. So if you need to, you can pause the video. But the critical value for a 98% confidence interval, make sure you can find this on your own if you look at your chart, is 2.326. So the margin of error then can always be found by taking that critical value and multiplying by the sample standard deviation. Okay. So notice we get a much bigger error this time, 5.3498. Okay, that shouldn't surprise us because we're asking the information to be even more accurate. Okay, or we're trying to be even more confident than we were before. All right, and so then my answer, so the 98% confidence interval for the population mean is going to be that 7.1, but this time plus or minus 5. Where was my number? 5.3498, sorry. I lost it for a minute. Okay, so in other words, we're give or taking this error amount. So if you work that out, if you do 7.1 minus this number and also 7.1 plus this number, you're going to get, and I rounded it to 1 decimal place. Math Connect will tell you how it wants you to round it. So notice we got a lot wider, right? So what that means is if our sample population has a 7.1 mean, then our population mean, which is everything, would 98% confidently be between these two numbers. Notice how far apart they are, right? Like that's a pretty big window to kind of deviate out from 7.1. So, all right, so I want you to try one on your own. So I want you to pause the video, see if you can get it. Using your table and all that good stuff, and then we'll see where you're at. So pause the video and then come back to this when you feel like you have an answer. But once you figured out your answer, okay, we'd want to look at the chart to find the 99% confidence significant value, which looks like 2.576. So the margin of error is going to be that 2.576 times the given 2.3, which is 5.9248. And so here is the answer. The 99% confidence interval for the population mean based on the sample mean is going to be 7.1 plus or minus this 5.9248. Or something between 1.2 and 13.0. Okay. So notice the more confident we want to be, the further our interval is going to spread out from what we got in the sample. Okay, so the more confident you want to be, the larger you're going to have to make your interval. Okay, So before we move on, we're going to look at some new notation, and I don't want you to be thrown off by it. So we've been talking about z-score, but there's going to be kind of a variation of z-score. So let A be any number between 0 and 1. Or another way to say that is A is between 0 and 1, like that. Then if you see the notation Z with a subscript of A, it refers to the z-score with an area of A to its right. Okay. Notice right rather than left in this case. The chart normally reads left. However, the notation Z A over 2, sub A over 2, subscript, refers to the z-score with an area of A over 2 to its right. And we're going to be using this z-score with a subscript notation off and on, so we want to learn this. All right, so let's look at an example. We're going to kind of map out how to use this new notation. So what if I said to find the critical value Z sub A over 2 for a 92% confidence interval? Okay. Notice 92% is not one of the values found on the bottom of the 8.3 chart. Okay, it goes 20, 50, 80, 90, 95, and then 98, 99, and so on and so forth. Skips over 92 altogether. Okay, so first we do need to figure out what A is. Okay, so notice it's a 92% confidence interval, right? So A would be whatever 1 minus 92% would be. In other words, 0.08. So what that means is that A over 2 is going to be half of that, or 0.04. Think of it this way. This is like you have 92% in the middle, and so what percentage would be outside of that? It would be 8%, which would be 4% on each side. Okay. So here is where we switch back to our old tried and true table. Because we can't find our given confidence level on the 8.3 chart, we need to find the Z value that is closest, or the Z-score that, let's say it like this, the Z-score that corresponds to the area closest to 0.04. Okay, so we don't use our 8.3 chart. We need to use our 8.2 chart. Notice we're going to have to use the second side. Which I thought I had a two-sided chart there, but I guess I don't. All right, so here's the back side of that handout I gave you. So you want to find the closest thing to 0.04. Notice right here we have one that's real close to 0.04. So look on the negative side, and the closest thing you can find to 0.04 is 0.0401. And that corresponds to a z-value of 1.75. Okay, so using table A.2, we can actually find any critical value, whereas A.3 just lists some really common critical values for some certain confidence intervals. So if you find your confidence interval is not on A.3, then you have to look at A.2 instead. All right, so let's look at an example where maybe we have to figure out more of the information. I'm not going to give you as much of it. So let's say we have a sample size of 80. And that sample size of 80 is drawn from a normal population whose standard deviation is sigma equals 6.8. And let's say that we also know that the sample mean is 40.41. Okay, remember this is the sample mean, right? We actually don't know the population mean, okay, because maybe there are too many values. So part A, I want you to construct a 90% confidence interval for mu, in other words, the population mean. Okay, so in the previous example, in example 1, I gave you a lot of this stuff. In this one, you're going to have to figure it out yourself. So first you have to find the standard error, which the formula for that, remember, is sigma over the square root of n. Okay, we know sigma is 6.8. Our n is 80. So we're going to need to give ourselves some decimal places here, but I get approximately 0.7603. And then I can look at my table, A.3, to find the critical value for 90%. We already did that one in example 1, actually. It is one of our standard ones that's available on A.2. So remember, our critical value, our value of importance, in other words, is going to be 1.645. So we're using all of this in order to find the margin of error. Okay, remember the margin of error is always critical value times that standard error. Okay, and so that works out to be, if you use your calculator, 1.2507. Okay, remember this represents the error, one way or the other. Okay, either too big or too small, that's our error. The 90% confidence interval of the population mean is going to be our 40.41, give or take our error. Okay, and if you work that out on the calculator, you're going to get something between 39.16 if we round to 2 decimal places and 41.66. Okay, so again, to recap, In our smaller sample, we got an average of 40.1, but if we want to make judgments on the whole entire population mean, we're going to have to expand it to say we can be 90% confident that since the sample had a mean of this, the whole population will have a mean somewhere in between these two guys. Okay. And of course, if we want to be more sure, we're going to have to extend that interval or that window out further. Okay. So let's do one where maybe we can't find the value on the chart. So let me pick a percentage that is not on our chart at all. So let's say I wanted to construct a, sorry, my tech issues here. Let's say I wanted to construct a 70% confidence interval. Of the population mean. Okay, so we kind of use example 2, and so we do want to go on both sides kind of. So this is what we would say. We would say, okay, A is going to be 100 minus the 70%, which would be a difference of 30%. So A over 2 is going to be half of that, or 0.15. Think about 70% in the middle, right? So 30% would be outside of that, 15% on either side. Okay. And then we're going to use table A.2. to find the closest area to 0.15 and the corresponding z-score. Okay, so the closest thing to 0.15, if we look at our chart, looks to me to be 0.1492, which corresponds to a z-score of 1 point, and it's on either side, so the negative is kind of unimportant since it would be on the positive and the negative side. It looks like 1.04. Make sure that's right. 0.1492 is definitely the closest. Yeah. Okay. So now that we have the critical value, or the important value, now we can do our margin of error. So our margin of error would be 1.04 times the 0.7603 from above. So I didn't do this one ahead of time. 1.04 times 0.7603 is 0.7907. Okay, so notice our error is smaller, and that should make sense to us because we're not having to be as specific, right? 70% is not as specific as 90%. Okay, and that means the 70% confidence interval. So if we only needed to be 70% certain that we were going to include the population mean in our interval, it would again be 40.41 plus or minus that error. And so let's do 40.41 minus the 0.7907. So that would be 39.62 if we round it. And then if we add it to the 40.01, add that error, we should get 41.20. Okay, so if we can be less specific, sorry about that, if we can be less specific, then we don't have to extend the window out very far. Okay, notice we're a little more compact there. Okay, but let's say that you want to be accurate enough, you know how accurate you want to be, and you want to find out how many people or how many values you need to survey in order to get a certain confidence level. In other words, in our IRS example, there are millions of taxpayers, right? So if I have to be 99% sure, then how many taxpayers am I going to have to survey in my sample to make my sample be accurate enough to predict my population? Okay. And this formula is going to look harder than it is, okay, just because it's got a lot of weird letters in it. So first of all, it's n equals, because n is what we're trying to find. And it's going to be the following. We're going to take the z-score we get from table 8.2, and we're going to multiply it times sigma. And then we're going to divide it by m, which is the margin of error, and then square it. Okay, so this is going to help us decide, you know, how big does the sample need to be? We talked about before that a sample is going to need to be sufficiently large if you're going to make assumptions from it. But how large is large? That's what this formula gives us. All right, so let's say that a population has a standard deviation with sigma equaling 17.3. And let's not do a part A, we'll just do one part on this one. So my question is, how large a sample must be drawn so that a 95% confidence interval for the population mean, which is mu, will only have a margin of error of 1.4. So I know how big my error can be, and I want to know how many values I need to sample to make sure that I get the accuracy that I want. Okay, so we're going to do n equals, and then we're going to have kind of a big thing here, right? So first is, what is the critical value? 95% is one that's on our chart. Okay, so you need to look back at your 8.3 chart on that last row, and the critical value is 1.960. Okay, and then we do the standard deviation, which is 17.3. and then divided by the error that we're willing to accept, and then square it. So all I did was plug everything into that equation right there. And you end up getting 586.6084. In other words, we have to have at least this many items. You're always going to need to round up here. I know this one would have rounded up anyway, but even if it's like 586.1, you would still bump it up, because in other words, you would need to go to the next item so that you had enough. Okay. In other words, 586 wouldn't be quite enough. We wouldn't be able to get the error that we were looking for. Okay, so it means that we would have to sample a pretty good size sample, 587, before we could get the accuracy that we were looking for. All right, so let's do one more question. It's going to have multiple parts. If you can follow along with this one and kind of pause it when needed, then I think you should be okay for the homework for this section. All right, so in a sample of 100 electronic components, produced in some company, the mean lifetime before this electronic component wears down is 125 hours. So we're going to assume that component lifetimes are normally distributed. In other words, we're allowed to use the charts we've been using with a population standard deviation of 20 hours. By the way, in the next section, the only thing that's going to be different is we're not going to know this standard deviation. Remember how the title of this section was standard deviation known? The title of the next section is standard deviation unknown, and that is where maybe we don't know what the population standard deviation is, okay, which is actually more practical. A lot of times, because the population is so large, you wouldn't know the mean or necessarily the standard deviation of that big population. But that's just looking ahead. But let's say I wanted you to construct a 98% confidence interval for the mean battery life. Okay, so remember, when you're trying to find critical values, you can either look at 8.3 at the last row, as long as that's one of the percentages that are included. 98% is one of the percentages. Or you can look at table 8.2. Okay, but I want to kind of show you that you actually could do either. Okay, so let's talk about that for just 1 second, and then we'll do it the easy way. Excuse me. So notice if you did 100 minus 98%, you would get 2%, and then if you divide it by 2, you get 1%. So if we look at this chart and find the closest thing to 0.01, it looks like maybe that is the closest. Okay. And so we end up getting a z-score of about 2.33. And notice that's exactly what we get here. It's just this is a little more accurate. Okay, so on the bottom row here, notice it's 2.326, which would round to 2.33. So use table 8.3 if your value is listed. If it's not, you just use table 8.2. All right, but moving on. This one is listed, right? So we're going to need to find the standard error. The standard error is going to be sigma over the square root of n. So it's going to be 20 over the square root of 100. So we end up just getting 2 there, right? Okay, so the margin of error, remember, is the critical value we get from the chart, which is 2.326 times the standard error of 2, which is 4.652. Okay, so this is our error. And so if we want to find the margin of error, we do x bar plus or minus that 4.652. So if you do that, you're going to get, and we're going to round it to the nearest whole number on this one, you're going to get something between 120 and 130 hours. Okay, so if they were trying to make judgments on all the electronic components made by this company, in other words, the population, they could be 98% confident that it'll lie somewhere between these hours if we round to the nearest whole number. All right, so without actually figuring this out, I want you to think about this. So if the confidence level were 95% rather than 98%, would the margin of error be smaller or bigger? Remember, margin of error is just the error one way or the other. So this is more of a conceptual question, and I don't necessarily want you to actually figure it out, okay? What I want you to do is think about it instead. Notice 95% is not as accurate as 98%, right? So we're not being as particular or as much of a stickler on what we have the value to be, right? Which means the error is going to be smaller. Okay, so the answer is smaller since a decrease in the confidence level will in turn decrease our critical value. In other words, we don't have to go out as far because we're not having to be as certain. And remember, our critical value is Z sub A over 2. And it's A over 2 because we're splitting it up left side, right side. That's why it's A over 2. And then last but not least, I want you to find the sample size needed. So that a 99% confidence interval will only have a margin of error of 3. Notice in real life settings like this would be very dependent on what kind of thing you were testing. Okay, for instance, if I'm studying a new drug that's supposed to cure people, I am probably going to want a pretty good confidence level, right? That my drug wouldn't cause someone harm. Okay, and so I might go even higher than 99%, unless we're just willing to, I don't know, sacrifice some of the people trying our medicine, which usually we're not supposed to ethically want to do. So our formula for N, remember, is kind of large. So first you look at your table to see if 90% is one of the values on the bottom row of table 8.3, and it is, and it's equal to 2.576. Okay, and then you multiply by the 20 on top over the margin of error of 3, and then you square it, and then you bump it up. So if I do that out, let me work that out. So I get 2.94 or 294, sorry, point something, and so it would be 295. In other words, if I'm going to want to be 99% confident that my error isn't more than this, I'm going to need to sample more than the 100 electronic components. I'm actually going to need to sample 295 of them. Okay, so in this section, I really want you to practice using 8.3 when you can, switch to using 8.2 when you can't, but really try to understand that this number that we're getting here represents the error one way or the other of the sample mean. Okay, and we're using this to predict the population mean.